Titan is one of the most fascinating places in the solar system. It is the largest moon of Saturn, the second largest moon in the entire solar system, and yet it has a thick atmosphere dominated by nitrogen. It has rains of methane, lakes, rivers, a complete hydrological cycle, but made with methane. And of course, NASA's Dragonfly mission is going to be heading to Titan in a decade or so to help us understand more about this fascinating world. My guest today is Dr. Sam Birch. He's an assistant professor at Brown University, and he is one of the writers on an upcoming textbook about Titan. Specifically, Sam focuses on the liquid on Titan, these lakes, rivers, rains, weather systems, clouds. And of course, this is something that I am fascinated about. And so I wanted to talk to Sam about how the methane works on Titan. All right, enjoy this interview with Dr. Sam Birch. Sam, what is the most interesting moon in the solar system and why is it Titan?
So Titan is, it is Titan, to answer your question. Why?
Yeah, obviously.
There's a lot of reasons why. I think one thing is that it's a place for everybody, every planetary scientist in the solar system. If you study chemistry, organic chemistry, geophysics, planet formation, dynamics, geology, hydrology, atmospheres, it has everything. So it's the most Earth-like planet in the solar system. It has this active hydrologic cycle where it rains, rivers flow today, waves are crashing on the coast now. Mars used to have that, maybe Venus had it, but Titan has it today. And yet everything, when we look at it, yes, it looks the same and these processes are the same, but all the materials are different. And you're at 10 AU, gravity is 1/7, and so it's a fun playground for all planetary scientists to study kind of the fundamentals of how things work in our solar system.
One of the things that really fascinates me about Titan right now is that our understanding of this world actually comes from a fairly limited set of observations. I mean, we have the initial Voyager spacecraft when they did their flyby. We have Cassini-Huygens. We have the descent of the Huygens probe through the atmosphere of Titan to land on the surface, some ground-based, space-based observations, and that's kind of it. Obviously you need more, but what are some of the kind of amazing things that people have discovered about Titan with this kind of lack of ways to really see the world?
So prior to Cassini, when we had Voyager, we knew of Titan. It was this big orange ball. The pressure and temperature at the surface made it possible where we could have liquid methane or natural gas condense and rain out to the surface. And there was theoretical predictions on, hey, maybe there's oceans of methane, or once they started looking and they're like, maybe there's not oceans, but maybe there's crater lakes of ethane. And that was stuff Carl Sagan speculated on way back. And then once we got there, we had all these questions and we came away with more questions. We had a lot of answers. It turns out there were liquids, but they were at the poles. It has this global desert. But really, we've come out of it. We know of where all the big things are and the big processes and what they're happening, but all the details of the rates of how stuff is happening, all the fine scale features that you'd use typically to understand a planet's history, we just don't have those. But what we did get with Cassini was spectacular. We were there for 12 years? Which is almost half of a Titan year, which is also half of a Saturn year. And so we got there in southern summer, saw all the way through the equinox, and then we saw northern summer just starting to kick up, and then Cassini was ended. The discoveries, there's a lot. Most spectacular ones, the one that comes to mind is when we were looking for waves. So we saw these lakes and these seas for scale are enormous. They're bigger than the Great Lakes. If you're standing on the coast or if you landed in the middle of one, you would just see open ocean on the side of you. It would be kind of freaky. And when we first looked at them for the first 6 years, they were dead flat, like mirror flat, which is hard to do for something so big where gravity is less, the fluid is a little more slippery, and the pressure of the atmosphere is higher. So theoretically, waves should be much easier to kick up. And we saw nothing. And so there was this observation planned where the spacecraft was flying over one of the northern seas. and it would look straight down and then fire off a radar signal, and then fire off a radar signal to the side, and then straight down and then off to the side as it went across the surface. And the idea is if the surface was rough, you would get a big return when you looked off to the side because part of the liquid is oriented towards you, and that's waves. They saw no waves. But when they looked straight down, the signal went all the way through the fluid, hit off the seafloor, and came back to the spacecraft. And what they're able to do was measure the bathymetry, or the depth of the sea, and measure the composition by accident, and a measurement that was thought to be impossible.
So sorry, was that surprising that I guess methane is, this liquid methane on the surface of Titan is essentially transparent?
Yeah, I mean, it was more transparent than we thought. Some initial laboratory studies weren't entirely correct, as it turned out. But the fluids are methane and ethane together. They're they're miscible is what it's called. So they mix perfectly. Our first observation of the composition came from a separate instrument, which measured just the very, very top layer, and it was ethane. And that's what the predictions were. Over time, ethane should build up. It's less volatile, or it's harder to evaporate. And so it should build up over time. And so our first observation was ethane. It's like, great, they're ethane. We shouldn't be able to see through them. The fact that they're you can kind of see in the images that they're transparent, people are like, they must be super shallow. And then once we got the bulk measurement, it was almost pure methane, and they're much deeper. And it's like, uh-oh. But also a huge opportunity. And then we spent the rest of the mission, we made 4 more measurements of the sea depths and compositions. The time mission, I don't know if people remember this, but in 2013, 2012, there was a mission to send a boat to Titan to measure the depth and composition of the seas. It didn't get picked, and it turned out a couple years later, Cassini was just able to do it. So I think that's the most spectacular example of how Cassini worked. It was just such a spectacular team to be on because it was very flexible, and they responded in real time to discoveries. And as we went in, we had an idea of what we should see. And Titan keeps surprising, even today, it keeps surprising us. And to have a team that was flexible and willing was really special.
Yeah, I mean, I feel like I'm reporting on a couple of Titan stories a month on data that ended when Cassini ended its mission. And yet, there's so much there that people are still finding really interesting discoveries in it.
Yeah, I mean, we picked the low-hanging fruit, if you will, of figuring out where things are and sort of what things are. But as soon as we're starting to dig just a little bit deeper, it's like, oh my God, that doesn't work this way, it works this way. And there'll be whole careers and PhDs for the next 20 years still digging through this data because there's a lot. Compared to other planetary bodies, it's not a lot. But I think it's, in terms of data volume, it's not a lot. But in terms of the richness of it, there's a lot to offer.
So I guess based on all of this, these data that have been gathered over the decades now with all the different missions and so on, give us a sense of what what is sort of like the climate, the larger climate on Titan.
Good question.
Yeah. I think about, I live in Canada, on the west coast of Canada, and we have, I live in a temperate rainforest, and in the spring and fall, we get large fluffy clouds. We get the rain starts in October, November. It gets pretty heavy until sort of January, February. Things kind of chill out. It gets very cold, but it's not very rainy. And then things pick up again in the springtime. And then by about May or so, the rain generally cuts off. And then we have clear skies through till September again. And it's this, but when it rains, it just rains day after day after day.
So what we know from the climate, the things we've observed that we can pull out, is we've tracked clouds all across Titan. So Cassini was able to observe tons and tons of clouds. And there's some surface features that you can use, like the distribution of rivers or where the lakes and seas are, or sedimentary deposits that tell you hey, it must have rained a lot here at one point. And so all of that is used by climate modelers who are then very creative and very smart to then tie all that evidence together self-consistently. And I think the picture that's kind of emerging is you have this 28 or 29 year, right? And it's generally pretty dry. And Titan, not much is happening most days. There might be like very light breezes, like that type of breeze. At the poles, it might mist a little bit and pretty consistently misting, kind of like Seattle, Vancouver-y. But then every once in a while, what will happen is that you'll get these massive, massive, massive storms that last for like 1 or 2-ish Titan days, which is a month on Earth, because Titan rotates very slowly. And so the way to think about it is not much is happening because you're like building up methane in the atmosphere like a battery, and then you discharge it all at once. And when you do this, you're getting like tens or 100 inches of rain over a month. So for scale, there was the hurricane that hit North Carolina. They received 30 inches of rain. So it's like hurricane levels, but it's for a month straight. So just pouring and pouring and pouring. And then it dries up again. And you'll get 1 or 2 of those storms per summer. And Cassini it's kind of consistent with the big, big clouds that we see on Titan. They're the size of a hemisphere. We can see them from Earth. The whole disk of Titan brights up, and those clouds persist for like a month, and then they go away. And what that would then mean for the landscape is not much is happening most of the time, but then when it does happen, oh boy, are our rivers filling up. Waves are going to be crashing like crazy against the coastlines. When you have all this methane, you're also going to have a lot of wind. And that's probably what Titan is. It's not like a desert in that, like, when you have a storm in a desert, it's very quick. It's more like a prolonged desert. And then all of a sudden it becomes very like tropical and just pouring and pouring rain. And then it's back to a desert again. So it's very bursty.
But it's all methane. And that's the part that's so bizarre. And so like, does methane rain differ from the kinds of hydrological cycles that we're more familiar with?
Because the fluid is different, so the properties of the fluid are different, gravity is less, and the atmosphere is much denser than Earth. Raindrops can be bigger and they fall slower. I can't remember the exact how much bigger, but they're like that big-ish.
Right, marbles.
Yeah, they're like little marbles that fall very, very slowly, such that you can like almost dodge them if they're falling, which would be kind of a surreal sight. When they hit the ground, they're also hitting with less energy. So it's like very bursty, but very slow. It would be a really surreal sight to see.
Yeah, but you'd be like on this landscape with slow motion marbles dropping all around you.
But then the river, if you're standing next to a river that's flowing, it would still be going the same speed as like a river on Earth. Like a meter per second is the typical speed that they move. So if you look out, the river would be behaving the same, but the rain around it would be in slow-mo. So it would be really weird.
Yeah. People are very familiar with the Dragonfly, which is going to be flying to Titan. And that's amazing. I mean, we're going to have this nuclear-powered helicopter flying around on Titan, an RTG-powered helicopter. But it's going to be sticking around the equator, not moving to to see this liquid. What are you sort of expecting to get out of the Dragonfly mission?
Great question. Dragonfly is maybe the most exciting thing NASA's done since Apollo. That might be a very hot take, but they're flying something that's the size of the Curiosity and Perseverance rovers, except it flies from place to place. So it is spectacular. It's going to the equator because it's going to go look at where organic material from the dune sands could have met liquid water in an impact crater. So when you have an impact, it melts the crust, and on Earth you get liquid molten rock. On Titan, that would be liquid water. And if you have liquid water mixing with the organic dune sands that are on the surface, you can have some really, really interesting chemistry take place. So that's part of the reason why they picked the cell crater where they're targeting to go explore, because they want to explore how far chemistry went in such an environment that would be conducive to something like life. Not to look for life, but look at these pathways. They also went to Cell Crater because it's close to where Huygens landed. And it's almost 1 Titan year later when they get there. So if you're trying to design a mission, right, that's flying, you want to know what are the wind speeds? Is it going to rain on me as I'm flying? All these engineering type questions to make sure we can do it safely. And so because we know what the wind speeds are like 1 year ago, you can kind of design a system that could work. So that's partly why they picked Cell Crater as well. It's thousands of kilometers away from the poles, where all the stable liquids are today. It does rain, though, at the equator. We've seen it rain at the equator. One of these big storms we saw darkened a huge area that stayed dark for like a month. And so it definitely does rain. We see rivers at the equator, right? So when Huygens landed, it saw this river cut up landscape in the middle of a dune field. So yes, it's a desert, but it does definitely rain, and it rains hard when it's there. And so I'm super excited once we get to the crater rim to see the evidence of this. And there should be sedimentary deposits that we can go up and read. There should be river networks. It's not expected to rain because that's like the dry season, especially at the equator. And I think the hope is that it doesn't rain for most of the engineers. I hope it pours. We're sitting on the ground, to be clear, because that would be spectacular, right? You're sitting in the middle of an extraterrestrial storm, and you can watch the landscape respond to that. But that's unexpected. That's like a dream that I think about from time to time. But we should be able to look at the evidence of recent fluvial processes. Are there little shorelines next to the lake or next to the interior of the crater? Because when it's raining for a month, you might be ponding stuff. And when you're ponding stuff and winds are blowing, you might see evidence of beaches that once that liquid goes away, that stuff is still kind of sitting there. And so there's a lot of really, really cool fluvial geomorphology questions we can ask. There's even just a basic question of, once we get, what is the shape of the hill slopes in the crater rim? If you look at any picture of the moon from astronauts or Mars from the rovers, you have these nice rounded hill slopes everywhere. And when you look at Earth, you see that as well. On Titan, you might not have that just because of how the rock breaks down. And so you might have a very, very rocky landscape, which would be pretty alien. And so that would kind of be a dead giveaway where we can learn about the materials and how the rock is breaking down just from one picture of the shape of the hill slopes.
Now, you say the word rock, but I know that water is so cold that the ice takes on, rock-like. So are you talking about actual rock, or are you talking about water rock?
I still, even if it's been 10 years, 12 years working on Titan, I still say rock and water for the fluids. No, so the fluids are methane and ethane and liquid nitrogen, and the rock, the stuff that if you're standing on there and crunching as you walk around, is frozen water ice. It has the same properties kinda as sandstone on Earth. So it'd be a nice, very competent, hard rock. There's also a second source of rock on Titan, and that's this organic sediment raining from the atmosphere. It rains 1 micron, so like less than a human hair per year. But over geologic time, you can build up quite a deposit. And that's what the dune sands are made out of. If you can lithify and like compress and squeeze those dune sands, you can make a sandstone on Titan made out of organics that also could get then eroded. But generally the rock is like probably water ice mostly, especially around the crater rim if you're walking around there. The methane rivers are eroding into water ice bedrock.
Right. But there wouldn't be any place where there was actually, say, silica rock the way we think of it on the moon or Earth.
No, yeah. All the silicate materials in the core of Titan. It's deep, deep within the interior.
Right, right. That is, I mean, I can see why it's almost like it's so alien to wrap your mind around that your imagination has to go and hold on to the things that are a lot more familiar here on Earth. Like, oh yeah, it's going to be a river basin and you're going to see sedimentary rock and you're going to see layers and you're going to no, it's methane rain going through layers of organic material that's been turned into sediment through water ice that is behaving like rock.
Yeah, it breaks your brain sometimes.
Yeah.
And you want to be careful not to be like, oh, it's like Earth, therefore it is on Titan, which you can do, say, if you go study Mars, right? It's silicate rocks, it's water that was eroding it. But on Titan, a good example of this are the fluids. So I said it was methane and ethane, but you also dissolve in atmospheric nitrogen depending on the temperature. And if it gets just a few degrees change can change how much you dissolve in, and that can change the density of the fluid by 20%. And on Earth, the densest water is super salty, cold, salt water. That's 2% denser than the least dense water on Earth. You don't get those contrasts. On Titan, you get these huge contrasts with just a small change in the temperature. So if you rain out a little cold and that methane is flowing across the surface in a river and it warms up a bit or cools down a bit, it could get denser or less dense. And if it's carrying sediment, all of a sudden, boom, that falls out. Or when it hits the sea, it's stuff that we're working on now, it can plunge all of a sudden, which rivers don't do here on Earth. And so the amount of dynamics that change is a lot. And that's basically all the stuff we're doing now of it's okay, you have a river, but let's change all the properties of the river and it can behave very wildly. What would a river then do to the landscape?
Yeah.
And you can do that with any number of things. So that's
think
why
about
I
glaciers. Think about,
right.
Think about, I don't know, all that organic material, and then the interesting chemistry that might be happening as it's interacting with ultraviolet radiation coming from the sun and a constant influx of methane coming into it and the interface between that and the water ice.
And that's where probably a lot of the stuff, if you're seeing it now, a lot of really good work is being done by people. Just what is this stuff and how does it behave on Titan conditions? If I take these organics and stick it in methane, what happens? Basic questions, you would think that they're basic, but they're really hard to answer. And it takes really creative, clever people to do that and to do it safely too. Because these materials are not nice to play with as well. So that's a lot of really exciting stuff is done by the experimentalist people. And then we see their results and we're like, oh, cool. Okay. What does this then mean for the dynamics of the river? And then you go back to the data and you're like, oh, actually, maybe we are seeing this. And it's this forever iterative process that is continuing to get richer and richer.
Right. People are simulating Titan in the lab.
Yeah.
Yeah. Oh yeah. Now, one of the things that I really consider to be a bonus is, people are really excited about, say, Europa, where you've got this shell of ice surrounding a liquid ocean, Enceladus, where the water is being sprayed out into the but with Titan, it's the same thing in that there's probably a solid core, a liquid ocean of water surrounded by a layer of ice, surrounded by all of this methane type activity. Do you think that there's any kind of mixing from that surface layer into that subsurface water ocean?
That's a great question. And my answer is I don't know. And I'll clarify why I don't know the answer to that. Generally, it's hard to mix stuff from the surface of an icy shell down into the ocean. And you can just have an ice cube in your cup and try to make it stay at the bottom of the cup of water. It's going to float to the top. You have to make the ice really, really dense. And one way to do that is with a lot of salt. And that's why detection of salts on Europa is important. Dynamically, it's still very, very hard to do. You might have an impact crater come in and punch all the way through the crust. That's one instant way to do it. But in terms of any crustal convection process, it's generally really hard. And it's nice to get those materials that are on the surface of Europa down into the ocean, because that's when cool prebiotic type stuff can happen. Enceladus is probably delivering all that interesting stuff to the ocean from the core itself. And so it doesn't need to bring stuff down. And Enceladus is amazing because it's giving us those free samples. All we got to do is go sit and collect them. Titan is also getting stuff from its core, not as efficiently as Enceladus maybe, but over geologic time, it's still getting the same amount of stuff, the really good organics, all that fun stuff. It also could have a pathway to get stuff down to the subsurface, which is what the other ones might not have. So you might have organics from the core and organics from the surface, both feeding into that ocean. And so that ocean could be very, very interesting. The problem with Titan is not problem, but its ice shell is very, very thick. Enceladus is like tens of kilometers, maybe 80 kilometers. Don't quote me on that number. Europa's is thinner. There's recent estimates that said it could be actually quite thick. So we'll see when Clipper gets there.
Yeah, 10 to 100 or something like that.
Yeah, it's a big,
wide range.
Whereas Titan's is like generally people are like, yeah, it's probably 100 to 150, but it's not less than 100. So that's a thick ocean to get through. And so if you want to go study that, you need to either have it be brought to the surface through some sort of volcanism, or you need to get through it. And on Europa, it looks like there's stuff that's brought to the surface, which then you can go sample. On Titan, I don't know if we see that. And so in theory, Titan's ocean should be super, super, super interesting. Whether we can go beyond just theory and experiments and test that, I don't know. I don't know how we do that.
I mean, I guess the hope is that there's some kind of seep that is coming upward, right? Where you've got liquid somehow being forced to the surface through channels and subsurface pooling or whatever. And then ideally some kind of cycle where then that organic material is then making its way back down. And it doesn't feel like there's a viable, apart from the occasional asteroid strike, there isn't a viable way. Even those probably don't dig that deep.
There's one cryovolcano, so a volcano that erupts liquid water. So cold volcano, if you will, on Titan.
Oh, interesting. Okay.
It's called Sotra Patera, or Doom Mons, after Mount Doom in Lord of the Rings. All the mountains on Titan are named after mountains in Tolkien's universe, which is fun.
That's super fun.
So there is one. I don't know if we have the data to say. If we could go back with a better orbiter, then we can really answer that question and go look for those places. There should be a way to get stuff out, though, generally on Titan, whether it comes up in a detectable amount that we can then go pick up and sample and look at for all the good stuff that it contains. I don't know, but stuff does get out probably because Titan has its atmosphere. So the methane only is stable for like up to 100 million years. And so on long solar system timescales, that's a blink of an eye. And it shouldn't have the methane. So either we got really lucky and we just happen to be viewing Titan when it has an atmosphere and is going away, or there's a resupply mechanism. And that resupply mechanism would be the interior. And you can make a lot of methane in the core and then leak that out to the atmosphere. So in theory, you are, well, if the atmosphere is old, which is a huge unknown, then you have a way of getting stuff out, but depends how much you get out.
So what would be a mechanism for you to get a recent atmosphere, like a comet hitting it or something?
Or something in the Saturn system. There was a recent paper on the formation of the rings of Saturn, because the rings in Saturn are really young. So maybe when that formed, the whole system was kind of going crazy, and you have all this methane stored in the ocean, and a big impact comes and you kind of get a one-off event. Maybe that's me making stuff up.
Right. But I guess the more established scientific consensus is that there is some kind of seepage of methane coming from the interior of the planet, driven by some kind of volcanism that is then continuing to replenish the atmosphere.
Yeah, and on Earth, You also have like a resupply of CO2 to the atmosphere through volcanism. It's sequestered in rocks and then re-erupted, and you get this nice stable cycle. On Titan, maybe you have something similar, where you have a way to sequester the methane, but then bring it back out. That's active research that, I don't know. We're basically at that level of drawing it on a napkin. And
Right. Yeah. But is that the kind of question that Dragonfly could help answer?
I don't know.
I wonder what it would take to know whether or not the atmosphere is getting replenished. I guess you could try and, do some kind of mass spectrometry on the particles and try and figure out, are they new or are they old?
I don't know. I know, well, more data will help.
Yeah.
The big unknowns in Titan science are basically, is the atmosphere young or old? What is the surface made out of, right? In theory, like the crust is ice, but again, all these organics are there. And Dragonfly will answer that one. Dragonfly is going to nail that one because it's going to drill into the surface and then send the material through very sensitive spectrometers. So they will definitely get that. I don't know. Yeah, maybe if we can figure out what the stuff is, it'll help constrain models, but I haven't thought about that. I'm sure someone has.
Sam, what are you obsessed with right now?
The main thing that I'm obsessed with on Titan, at least, is when we look at the coasts, we don't see river deltas. And this is stuff that we've been working on the past few years. Most rivers on Earth, especially big rivers that deposit into the ocean, have river deltas. The vast majority, and especially big ones. I think with large rivers, the size of the ones we see on Cassini, every single river has a river delta at the end of it. On Titan, when we look at the rivers, you see these huge Mississippi, Nile, Rhine River sized, huge rivers, and they hit the coastline and there's nothing. And it's, as a geomorphologist, it's very disappointing. And so we have a bunch of hypotheses of, okay, why is that? Is it because Cassini couldn't see them? Because again, it's a terrible instrument it's amazing, to clarify, but not an ideal instrument for looking at coasts. And so we said, hey, if we looked at Earth the way we look at Titan with Cassini, could we see it? And the answer is yes. And so that's not the problem, is that river deltas truly are rare. There's one river in the south that has a river delta at Ontario Locus. That's it. And so they're truly absent. And then we said, okay, maybe the rivers are bad at transporting sediment. And the answer to that was like, nope, they're better than Earth, because the sediment is more buoyant and mobile. So it's like, okay, no, not that one. The ones we're working on now is like maybe wind and waves. When you dump the sediment at the coast, it carries that sediment away along the coast faster than you can form the delta. That's one that a student is working on now. Another one is if you have sea level that's going up and down, because Titan has long-term climate change, just like Earth, that maybe you're flooding them at the north where we don't see any deltas. And that seems plausible. And then the third one is because these fluids are so weird, maybe when the river hits the coast, instead of, if you look at a river, you see like these plumes of stuff going out. And that's because freshwater is more buoyant than saltwater. And so the sediment that freshwater river is carrying slows down, or the whole flow slows down because it's buoyant, it's running into a headwind, dump all your sediment. On Titan, the rivers might be denser and they'll just hit the coast and just keep going. They're like, I don't care that the sea is here, I'm just going to keep going. And we're doing some work on that as well. Trying to figure out like, why does Titan not have deltas? And it's a really fun mystery that's forcing us to think both traditionally how we think of how you would form deltas, but then also like, okay, we have this weird fluid with more buoyant stuff. Maybe it's just inherently hard.
So it's back to the boat then, I guess. You need another boat.
Back to the boat, yeah. So if you can sit at the end of one of these rivers on the coast and see what's coming out, that would be easy. That would make the job easy.
That sounds great. So I guess, not an orbiter, a boat.
Both.
Okay, both. An orbiter that deploys a boat. Fine. Well, Sam, good luck with getting more information. And, we're all going to watch with bated breath as the data starts to come back from Dragonfly. It's going to be revolutionary. And I can't wait to find out more about what is objectively the most interesting moon in the solar system.
Awesome. I agree.
Thanks.
Thanks.
I hope you enjoyed that conversation with Dr. Sam Birch. Now, as a bonus, I chatted with Sam about what is his ideal mission to go to Titan to help us better understand the liquid on the surface of Titan. Is it a boat, a sailboat, a submarine, an orbiter? You're going to have to find out. And of course, the conversation is over on Patreon. It's completely free, publicly available, but you have to watch it over there. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bowdy, Caradwin, Cy Nelson, David Gilton, and David Matz, Dustin Cable, Evan Pro, Greg Feely, Hen Schultz, Hudson Ward, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Lawrence Federico, Michael Purcell, Paul Rohrbach, Ren Kaidu, Robeck, Sean Sargent, Spiderswap.io, Stephen Fowler Munley, Thomas Elskadron, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. People always ask me, what is your favorite world in the solar system? And I have been pretty adamant that it is Titan. Titan, Titan, Titan. I can't get enough of Titan. We have this world that is far out in the solar system, and yet it has a lot of the same aspects of what might have been like the early Earth. We have organic compounds on the surface, rains of methane, and all of this is coming together in ways that could give us a sense of what it was like on Earth early on in our history as those organic molecules first arrived on our planet. And NASA is going to be sending the Titan Dragonfly, a nuclear powered helicopter. Okay, fine. It has a nuclear RTG, but still octocopter. But still, there's going to be a flying helicopter on Titan that is going to be flying around and examining the landscape in a way that if you think ingenuity is cool, Dragonfly is going to take that to the next level. And of course, I'm going to keep giving you more and more information about this mission as we get closer. Now, I've got lots of other interviews here on the channel about planetary science, so you're definitely going to want to check out some of those. All right, we'll see you next time.